Mother Nature is full of wonder, profound designs, systems, and miracles. And by diving into its secrets, we can figure out how to create a sustainable world. If we look at life in cities, we would find it becoming more depressing and tight due to population growth and pollution from human activities. Therefore, people have to find ways to make their life better. And one of these ways is gardening. Gardening has been viewed for its wide benefits to people and to the environment. For example, it contributes to 1/3 of fresh food production for cities. Besides its benefits to improve the physical and the mental health of people and educating the young generation about the environment. However, it is nowadays becoming more challenging to garden due to water scarcity and overuse of water. If we look at some of the statistics, we would find that garden irrigation counts for 30 to 56% of the total household water use in Australia, USA, and Spain. If we move to the Middle Eastern countries, particularly the Gulf countries, the situation is even worse. Why? Because of the limited water resources due to the climatic nature of the region, and also because these countries depend heavily on desalination water to supply domestic water uses for them. If we take the example Muscat, the capital city of Oman, we would find that it is heavily using desalination water for desalination water as a source for domestic water supply. Irrigation of gardens counts for 40% of the total, 45% of the total household water supply, which is again a desalinated water produced at a high cost and high energy. That's end up with a water cost of about 80.6 million US dollar per year for all Muscat area. Though people love to garden as they spend time to create their beautiful gardens and select a wide varieties of plants, as you can see from these pictures, but some of their activities makes gardening unsustainable. Besides their use of desalinated water, many they don't use any water saving practice, or some of them even do not differentiate in the crop water requirement for plants. So they give the plant the same amount of water in summer and winter, and they apply it for all types of plants. When we look at the challenges that they face, some of them listed that water bill, no person to take care, and limited time. These challenges were mind-opening for us, that if we really want to help these people, we have to come up with a system that saves water for them, hence reduces the water bill, and do not need anybody to irrigate. I mean, it's a self-irrigating system, so no need for a person to take care of the irrigation, and that would save them even time. We were inspired by nature to do this, by the discovery which was discovered in the vicinity of one of the recharge dams in Oman called Al-Khouth Dam. A research team discovered a 3D capillary barrier, which is different than the known capillary barrier. Why? Because this capillary barrier consists of fine blocks made of silt surrounded from all directions by cracks filled with sand. The uniqueness of this capillary barrier in its ability to intercept rain. So when rain happens, water passes quickly into the profile and then absorbed into the blocks. Then it will be saved there. When rainfall stopped and the soil starts to dry, capillary barrier works to reduce the evaporation losses and saves water. And this was clearly evidence from the vegetation, that vegetation growing under such a structure in the dam were growing healthily and green, and elsewhere where this structure do not exist were dead. To further improve the water conservation into the system, we combined the smart capillary barrier with a wick irrigation, which is basically a subsurface irrigation system. In this system, water is applied at the bottom let's say, a sand or gravels, then rises naturally by capillarity to the root zone. Our final design looks like this, which is basically a pot of a common size that people use. And in this pot, we have at the bottom a water tank, and at the top, we have the structure, the capillary barrier, the smart capillary barrier structure. And water wicks into the substrate by a wick cylinder, which is a perforated PVC pipe filled with sand. We were interested in this experiment to know the study and to study the water distribution and evaporation under the smart soil as compared with a control, which is basically a homogeneous soil, exactly the same design except that it does not have the smart capillary barrier structure on it. We were also interested to see the effect of the diameter of the wick cylinder, so 2.54 compared to 1.27 centimeter, and its effect on the imbibition and the wetting of the soil. Our design went through a lot of experiments and trials, started from the field until it transformed to started from the lab until it transformed into the field. We started, for example, with a capillary rise experiment to determine the appropriate height of the wick cylinder by which it supply enough water to the substrate. We designed a Marriott bottle, designing the pots, also perforating of the wick cylinder, designing a template to structure the smart capillary barrier, washing the sand to remove the fine particles, and the filling process. And our final design looks like this. So what you see here is the smart capillary barrier, which is connected to a Marriott bottle, and at the bottom you have here the storage tank, the water tank, and the soil structure up. And as you can see, it has some sensors at the top and at the bottom. The homogeneous wick looks exactly the same, except it does not have the smart capillary barrier structure, and it also was equipped with moisture content sensors to measure the volumetric moisture content. We run this experiment into two different phases, phase 1 and phase 2. And in phase 1, we just kept the soil surface as you can see here at the top. In phase 2, we added 2 centimeter layer of sand on top of the soil substrate in order to further improve the conservation of water into the substrate. Of course, these treatments were triplicated and randomized into the field. Each one of the phases consists of two different cycles, wetting cycle and a drying cycle. In the wetting cycle, the water was supplied by the Marriott bottle and maintained at 3 centimeters. So it is allowed to wick into the system. And we were interested to measure and evaluate both systems in terms of the time taken to reach a volumetric moisture content near saturation and also the water distribution. Once we approach and reach a constant volumetric moisture content near saturation and collected the data, we stopped the supply of water into the systems and then allow the soil to dry. And in this drying cycle, we were interested to know which one of these substrate dry at a slower rate, which means it conserves water. We also did some analysis for the soil texture, sand fractionation, bulk density, KSAT, soil pH and EC. We construct the pressure plate apparatus and collected weather data. These data were very important to be used as input for our modeling. In our modeling, we use Hydros 3D and to model the experiment, and this is, as you see, the geometry. We also use observation points at the top and the bottom, exactly at the same location of the sensors, and we imposed the following boundary conditions. So for the wetting cycle, we have at the bottom of the wick cylinder a constant head, 3 centimeters, no flow boundary condition from all sides, and atmospheric boundary condition at the top. For the drying cycle, where water supply is stopped, at the bottom we converted this one into no flow boundary condition, and we use the same boundary conditions for others. We also apply hysteresis in the retention curve, did some sensitivity analysis to determine the appropriate size of the mesh, and we found this size 2 centimeters more appropriate. we impose minus 500 centimeter as initial condition for the wetting cycle and minus 20 centimeter for the drying cycle. We also did some sensitivity analysis to determine the most sensitive parameters of the Van Gnechten parameters for the silt loam and the sand, which used as substrate for the soil. And we found that alpha and N for the silt loam were the most sensitive parameters. So from there, we try to calibrate our model by finding the optimum alpha and range, alpha and N, by which it minimizes these evaluation criteria, the root mean square error, and maximize the Nash-Sutcliffe coefficient and Wilmot index. And we found a good acceptable agreement between the model and the measured data. We also use some statistical analysis, three-way repeated measured analysis to compare the results. What we found in our study, let's start with phase 1. So as you can see here, you have graphs for the moisture content with time, showing the wetting cycle and the drying cycle. And it shows also the curve for the measured and simulated, bottom and top. And as you can see here, you have the smart soil with 2.54, and here you have the homogeneous ones, the control with 2.54, same diameter size. In the wetting cycle, we found that the smart soil wets the soil into 2 days. Homogeneous soil took almost double the time, 4 days, to wet the soil. When the diameter is changed to a smaller size, it results in prolonging the time for saturation, as you can see here. However, the trend is still maintained that the smart soil wets the substrate 2 times faster than the homogeneous one. And this is because of the presence of the sand layer in the soil. As you can see here, these sand cracks or sand-filled cracks facilitate the propagation of water and increase the surface area exposed to wetting in the soil, where you don't have them in the homogeneous way. For the drying cycle, it shows that the smart soils actually dry at a very slow rate, almost at 0.009 centimeter cube per centimeter cube per day, which makes the soil preserve around 44 to 52% higher volumetric moisture content as compared to the homogeneous one. For the phase 2, when we applied and when we added a sand layer on the top of the soil substrate, it did not actually affect the wetting cycle because the same trend is maintained. 2 times faster wetting for the smart soil as compared to the homogeneous one. However, it has an obvious impact, a significant impact on improving the water conservation and saving by minimizing evaporation in all the soil substrate. And this basically still makes like the smart soil conserve around 20 to 38% higher volumetric moisture content than the homogeneous one, the homogeneous soil, as compared to phase 1. Our finding of this study shows that the smart soil, the smart capillary barrier-Wick, is a promising technique to preserve water for home garden, particularly in arid climate area. Though our experiment was run with the absence of plants, we are now exploring the practical application of the smart capillary barrier without the wick, which is inspired from nature for application of farming and landscaping, and we find promising results of water saving. We also studying now the impact of smart capillary barrier on the secondary salinization and microbial diversity. The future studies would focus on investigating solute transport across the contrasting porous media, and also the enhancement of the soil fertility by addition of biochar into the blocks. At the end, I would like to acknowledge the fund and support from the funding agencies, and also the support from Sultan Qaboos University in Oman and the technical staff for their facilities and help. Also, I acknowledge the mentorship and help from the research group, and also I extend my appreciation to the families, friends, and everyone who contributed to the success of this research. So thank you very much for listening, and I will be waiting for you in the discussion session. Contact me.